Okay, physics from High Point. We are on section B, chapter 9, and it's talking about how does energy relate to work. So in the past, you recall energy was defined as, or not defined, described as the ability to do work. So energy, ability to do work. So if energy is the ability to do work, think of it this way. We have to put energy into a system to get work done. So let's take a look at this example here. I have a little car, has to get to point A, and then it has to get to point B. A force is continually applied. It's starting at 0 meters per second. So force is continually applied, so it can go an increase in velocity. Let's just say it increases to 2 meters per second. Then it increases continually at a constant acceleration to 4 meters per second by point B. In this chapter, we're going to take a look at the mathematical relationship of work, force applied across the distance, right, of work to the energy. We're going to start with the energy of kinetics. So in order to do that, we need to think about work or net work, right? So when we think about net work, okay, we're not talking about just work done to get to point A. We're going to talk about the overall network, and we're going to focus in on a force being applied between 2 points in a single direction on a line. And we're going to focus at constant velocity, but we're going to talk about the total work, net work meaning total work, done over a specific distance. So if we were to do that, we have a change in distance. So I'm going to define it as this. Work net equals the force applied across a distance. Not a whole lot different than what you've seen, but we're going to define difference in terms of velocity. All right, and you're going to see some relationships. I'm just going to put a little graph here. Force is mass times acceleration, right? And okay, so here we have our work graph, and we found the area underneath the graph is defined as work. So put a big W in there. All right, and we're going to kind of ignore the mass, the scalar aspect, and when we're going to take distance, mass, acceleration, and distance, and we're going to define those in terms of velocity. So I'm going to do it a little bit different than the book, but it's the same result. We're going to just take this force, I'm going to rewrite it over here. Work equals mass times acceleration times distance, and I'm going to focus on this acceleration piece right here. So I'm going to just put a little dot to kind of highlight it there, and recall that acceleration is equal to the final velocity squared minus the initial velocity squared over 2 times the distance. All right, so let's just say I want to do work, I'm going to define it as work net equals mass times this piece here is going in for acceleration, right? So V final squared minus V initial squared over 2D times the change in distance. We're going to cancel the distance out, all right? And we're going to be left with work net equals the mass times this piece here. All right, so I just got rid of the distance, and what I'm going to do is I'm going to distribute mass and this 1/2 expression. So 1/2 and mass to the first velocity, and then 1/2 and mass to the second velocity. All right, and so you can see if you're trying to remember this expression, you can think of certain things being done to the exponent, okay, half and squared. Or if you're thinking of algebra, a way to remember this is remembering this expression here. It's pretty much the way you'll have to remember that. If you recall from 9th grade, you may have recalled that we defined kinetic energy. We wrote it like that, capital K, capital E, is equal to 1/2 mv squared, and we simplified it like that. So how do we get from here to here? Well, just assume that one of these velocities is 0, and you basically get this expression right here. Let's see, what else did I want to go over? Give me a second. So you could say that the work net, the net work, is equal to the change in kinetic energy. All right, so the change of energy that needs to be applied to get it to go from point A to point B by applying force, right, and increasing this kinetics, this motion. Okay, you now have new motion. Let's take a look at something really quick. I wanted to show you my cheat. Looking for eraser. Okay, so I want to show you something where I kind of cheat to think about this. We spent all this time in chemistry talking about conversion and converting units, and a little bit of cheat. Let's squeeze that in right here. So work is equal to joules, right? That's our unit of work. Joules is derived from kilograms times meters squared over seconds squared, right? So if you took force times distance, you get kilograms meters squared per second squared. What happens when we use 1/2 times the mass times velocity squared? Well, we also get kilograms meters squared over seconds squared, right? Potential energy, if you recall, let's look at that. Let's just take our object and give a new definition here. Energy of potential is your energy of position. And it's usually a position relative to a force, so let's just take the force of gravity and make our point A and B going vertically. Sorry, A and B. So now we have a slight difference, okay? Work or change in work, work net, would be a change in height, okay, because we're changing height. We'd have gravity, right, against the force of gravity. And of course we have a certain mass that we're trying to move. All right, so this is where we're going to get our expression of potential energy, right? So if work is simply force, or sorry, mass times acceleration times distance, well then our mass is mass, that hasn't changed. Our gravity is our acceleration, and our change in height is our distance for the work formula. So if these are all the same, then we still have mass, kilograms, we still have acceleration, meters per second squared, and we still have distance of meters, so we still have our units that we need for joules. All right, so you can see that joules relates to work, but it's also the same unit for energy, whether it be kinetic energy over here or potential energy in that expression. So let me just finish with this expression here. Work net is equal to the change in energy potential, okay, and I'm going to write it like this. This is what the The variable the textbook uses, it's a conventional variable for potential energy. It just uses a capital U, and then you can put a subscript for gravity. If it's potential of a gravity, you can put an S. If it's a potential for a spring, change the potential of a spring. It uses a capital U. It would be interesting to figure out why we use U. It seems to me that nobody knows exactly why, but we've been using this convention apparently since the 1850s. So an expression we're just going to use in this class. And again, this is also a conventional form. The energy of potential may be something that you'll use in the future. All right, the last thing I want to go over is the next section in your textbook talks about types of forces, all right? It describes a conservative force, all right? And so it's going to give you some examples of conservative and non-conservative forces. I want to help you visualize that, and here's what I do. When I want to visualize or try to remember, how do I know if a force is conservative? Well, if a force is conservative, my energy of kinetics is completely transferred to energy of potential with no loss. Okay, it's 100. Think of a machine that's 100% efficient. There's no loss in friction. You have the perfect motor. It's 100% efficient. Okay, if something is conservative, a conservative force is being used. Energy of kinetics is converted to energy of potential without a loss of heat or sound or light. Perfect machine. I like to think of it as my perfect, never-ending roller coaster. Perfect roller coaster. Here's my cart. All right, my perfect never-ending roller coaster starts at the top of the hill, goes to the bottom of the hill, comes right back up to the same height, maybe a little bit higher to make that equal. Okay, my perfect roller coaster has this energy of potential. It's completely transferred to the energy of kinetics with enough speed to get right back up to the same height, to the same potential, okay? There's no loss in friction, right? There's no rubbing of the wheels. There's no loss in sound. You don't hear the screechy metal scraping. You don't hear the clicking as you're going across the seams of the roller coaster. The wheels and the rails don't get hot from the friction, so you have this perfect never-ending roller coaster that never slows down, and it always can get back up to the same height, because at any point on the roller coaster, for instance, if I'm halfway down, I'm going to have half my potential energy, and I'm going to have half my kinetic energy, all right, if I'm halfway down, all right? So everything is just smoothly, nicely being transferred from one type of energy to the other. So that would be one way to visualize a conservative force. Okay, that would be the conservative force of gravity on my perfect roller coaster. How about a perfect? Okay, in physics we have ideal things. The ideal spring, okay, is perfect. So here my elongation distance equals my compression. Okay, and I have this lovely spring that goes down and up and down and up, and it never ends, okay, because it's ideal. If the force is conservative, the spring never heats up, it never stretches or tears, it doesn't have a weight of its own, okay, so that would make it an ideal spring, a Hooke's law force spring, and that would make it a complete conservative force. All right, so if you have any questions, Zoom me tomorrow. Hopefully this helps you answer your questions from your guided notes. And and tomorrow I'll help you solve the problems.